NMR spectroscopy is really a bread and butter technique for a lot of different chemists, particularly organic chemists and sometimes even biochemists in the work in their research labs. That's certainly true here at Southern. A while back, I was able to work with one of my colleagues, Dr. Michael Hurst, and help him use NMR in a research project that he was working on in his lab. Now, Dr. Hurst did not use NMR very often, so he asked me to help him with it. And, naturally, I kind of hemmed and hawed and hesitated and whined and moaned and groaned a little bit about it. But eventually, got around, tore myself away from Netflix long enough to actually help him make up a sample and get down on the NMR spectrometer. He was interested in studying this molecule. It's called phenylglyoxal, and it's not something that he made but purchased for use in studying some reactions of this particular compound. And like a good scientist, he was interested in getting an NMR spectrum of this material first, just to make sure that what was in the bottle was actually what was said to be in the bottle was actually in there, and that the spectra we would obtain would match the expected structure. He had worked with this molecule years ago, I believe in graduate school, and had gotten some unusual or strange results, and was curious to revisit it years later and see if he could come to a greater understanding of what was going on. The structure of phenylglyoxal is a relatively straightforward one. And so when we looked at the structure, I made an inventory list of, here's what I would have expected to see in both proton and carbon spectra, just to confirm that knowing, again, the sample history, here's what we would expect to see in our spectra. And the thing that just jumps out at you is the aldehyde hydrogen. We should see chemical shifts of an aldehyde in both proton and in carbon. You see an aromatic ring here. It has 6 carbons total, 5 total hydrogens, but of course symmetry is going to play a role in this monosubstituted ring. We should see 5 aromatic hydrogens. We should see 4 distinct carbons. And then there's this other carbonyl group in here, which might be a little bit unusual. You don't often see carbonyls right next to other carbonyls like that, so that may be a little atypical, but otherwise it seemed to be a pretty straightforward structure and pretty straightforward what we should look for in our spectra. We found the material did not dissolve very well in deuterated chloroform. We got a little bit in solution though, and so we went ahead and ran the spectra, and this is what we saw. Now I point out the solvent peak in here. With a solvent peak of deuterated chloroform, remember it's right at 7.26 ppm, being this large, it is clear that the sample is not terribly concentrated. Your residual solvent peak should be a lot smaller than this. This is just a nice sign that the material did not dissolve well at all, but we did get a reasonable spectrum out of it. And at first glance, we saw the aldehyde peak exactly where we'd expect it to be. But I want you to notice, compare its integration with the aromatic region. The aromatic region integrates to 5, but the aldehyde peak integrated very low, only 0.15. I would have expected a 1 to 5 ratio here. Didn't see that at all. The other thing we see are 2 other peaks, one here at around 6 ppm, and this other broad one down here above 4 ppm. Now the broad one, that's consistent with water. This sample seems to be fairly wet. Hey, it happens, so that's not a big surprise. But 6 ppm, that's unexpected, and it was a little bit hard to figure out what that might be. It's certainly not an aldehyde peak. My first thought when I looked at that peak at 6 ppm was that maybe this sample is contaminated. It has some water in it, so maybe it has the contaminant. But it's a big contaminant, and in fact, what bothered me about it is it is the one that integrates 1 to 5 with the aromatic. If you have a contaminant, it usually doesn't integrate that high, and certainly not in these kind of nice, pretty whole number ratios that we're seeing here. So this was a puzzle. This really bothered me a little bit. Unfortunately, we weren't able to get any carbon spectra out of this sample. The concentration was just too low. And remember, when you do carbon, you're essentially switching from proton, a 100% abundant nucleus, to C13, a 1% abundant nucleus. In effect, you're cutting your concentration by a factor of 100. We just did not have enough in there in chloroform to get a decent spectrum. So we poked around a little bit and found that acetonitrile is a good solvent for this material, so we used some deuterated acetonitrile and headed back down to the NMR lab. So here's what the proton spectrum of the phenylglyoxal sample in deuterated acetonitrile looked like. Now this time around, you see virtually no aldehyde. There's a little bump over here, but ain't much at all. And you see the aromatic region, very nice, but now we see, in addition to water and solvent, two new peaks. One at 5 ppm, one at 6 ppm showing up. The chemical shifts of these two new peaks at 5 and 6 ppm made me first think of alkene, and in fact this is the structure I kind of sketched out as I was looking at the spectra, wondering if the phenylglyoxal was actually contaminated or had a lot of actually this alkene, this molecule in it. It would surprise me that it didn't dissolve well in the chloroform, but the chemical shifts seem to work out right. And so we kind of made a couple of notes that, what we should expect to see in the carbon spectra. And certainly we should see some alkene carbons. And in fact, in a DEPT 135, we should see a CH and a CH2 group if this alkene structure was really what was going on. So we were in deuterated acetonitrile. The concentration was high enough. We did obtain a carbon spectrum, and this is what it looked like. Right off, we notice there are no additional alkene carbons in here. Remember, the chemical shifts of alkenes tend to track closely with the chemical shifts of aromatics in carbon spectra. And so I expected to see these things around 120 or a little bit higher. We do see peaks there, 4 of them in fact. They are the aromatic ring that we see in the proton spectrum. 6 carbons, but 4 of them are distinct because of the symmetry of the monosubstituted aromatic ring. No other carbons in this area. We see the aromatic ring, we don't see anything else. Not good evidence for the proposal that we have an alkene sitting in here. And then there's this 1 carbon over here, consistent with an aldehyde, about 190, a little bit above 195 ppm. It's small, but it could be consistent with an aldehyde. And then over here on the other side, we have this 1 carbon at around 87 ppm. Not a common area for chemical shifts. Not quite sure when we were first running that what that one was. So we ran a DEPT 90. And the DEPT 90 spectrum shows a couple of very interesting things. One, the aromatic region. It shows 3 distinct CHs in the aromatic. There are 5 of them in the molecule. Symmetry means 3 of them are distinct. No surprises there. The aldehyde carbon, or what we thought was potentially the aldehyde carbon, the carbonyl group, is missing. Now, an aldehyde is the only carbonyl functional group that has a proton right on the carbon. And so aldehydes show up in DEPT 90s. They show up very nicely. The fact that it's missing that carbon that could have been an aldehyde carbon is not. It cannot be an aldehyde in there. Maybe a carbonyl, but it's not an aldehyde. And then the peak at 87 ppm. It's nice, it's tall, it is a CH. Then we ran the DEPT 135, and interestingly the DEPT 135 showed nothing new. It looked exactly like the DEPT 90. It certainly did not show a CH2 group, did not show a methyl. Therefore, conclusive evidence that my original thought that what we had was an alkene contaminant, toss that one right out the window, and it was back to the drawing board to think about what was going on with these with this molecule in these spectra. So clearly our sample was not phenylglyoxal, at least the way the structure was drawn. And it was certainly not an alkene or some alkene derivative of this. So we're left with the question, well, what is it? And so we went back to the proton spectrum, and I tried a D2O drop test. Yep, put a drop of D2O in, gave it a shake, let it sit for a moment, put it back in the magnet, and reacquired the proton spectrum. And what we saw was this peak right here at 5 ppm disappeared. In other words, these are two protons sitting on a heteroatom, not on carbon. The fact that these two protons are sitting on a heteroatom explains nicely why there is no CH2 that shows up in a DEPT 135. It can also explain their chemical shifts. Heteroatom protons can vary widely. 5 ppm is not an uncommon location for hydrogen sitting directly on an oxygen. We have two of them in this molecule with the same chemical shift, so they must be two equivalent OH groups. So after thinking about it a little bit, we propose that what we are seeing in this material is actually this equilibrium reaction, where the phenylglyoxal reacts with water, we see a lot of it in there, and forms this hydrate, okay, this hydrated version, where water not just is nearby, but water has actually reacted with the phenylglyoxal and made this hydrated version. And so if you compare the proton spectra with this, in chloroform, we seem to see some of the aldehyde and most, maybe 15% aldehyde and the rest, 85%, the hydrated version. When we go to a more polar solvent like acetonitrile, the reaction is even more highly favored in the hydrate form. We see virtually no aldehyde proton and no aldehyde carbon at all. The hydrogen integrating to 1 at 6 ppm that I thought was a alkene at one time, I now believe is the hydrogen attached to a carbon, not next to one oxygen, but next to two. One oxygen would bring it up to around 4 ppm, that interesting region. Two oxygens seem to be bringing it all the way down to 6 ppm. Yeah, it's invaded the alkene region. A good illustration that chemical shifts are nice rules of thumb, but please don't interpret them as a guarantee. You can have interesting things going on with these molecules. This equilibrium reaction also beautifully explains the carbon spectra. We have this CH that showed up in the DEPT 90, chemical shift at 87 ppm. The carbonyl that has a chemical shift that seems to be consistent with an aldehyde but vanished in the DEPT 90. It's this carbonyl here that is in an unusual position sitting next to this hydrate over here. And then of course the regular aromatic carbons that we're familiar with and know and love dearly. Altogether, I think it makes a nice little story of using the skills we've been building up so far in NMR spectroscopy. It uses knowledge of the sample, or what we thought the sample was going to be, and let's face it, the spectra is consistent with phenylglyoxal, but having reacted with water. It's a polar molecule, it seems to attract water, it actually seems to exist as a hydrate, which probably does affect its eventual reactivity, which may explain the results Dr. Hurst had seen many years ago in studying this compound. We used our knowledge of chemical shifts to make predictions and to try to understand the spectra we actually did see. We use our knowledge of chemical structure and number of groups and how symmetry, especially in that aromatic ring, can play a role here. We use some of our fancy techniques, the D2O drop test and DEPT 90 and DEPT 135 spectra, and all of that came together to produce this proposed reaction going on with phenylglyoxal and water that is beautifully consistent with the spectra. And it's just a nice illustration of the power of NMR spectroscopy to investigate and answer routine research questions.